Alright guys, so in this video we're going to go over chapter 2, sections 1, 2, and 3. So anytime we do a study in statistics, there will always be data and certain variables. And most of the time it is unorganized and we have to organize it into a table, we call frequency table or distribution table. And here is an example that will help us understand what I am talking about. A researcher played a mobile device game for 2 hours. The objective of the game is to capture as many virtual characters as possible. The following table shows the list of characters captured after 2 hours of playing. So the name of these characters are plastic, liquid, wheat, insect, metal. Just scanning to see if there's any more. And that's the problem. So I have to scan to see if there's any more. I have to look to see did I miss any. So the best way to take advantage of your data is to place it in a well put, organized distribution table. So how do we do this? Well, first things first is we have to identify our classes. We have to tally our classes, and the frequency is our count and the percentage of how much did we find. So I'm gonna classify the classes as each character. So plastic will be one class, wheat is another class, insect, metal, and liquid is another class. Tally is simply counting off, and you could just do it by hand, just simply counting off how many plastic, how many wheat, how many insect, how many metal, and how many liquid. So you just do a hand count pretty much. And your frequency is the numerical value of your tally. So I tallied 9, so my frequency is 9. I tallied 7, so my frequency is 7. However, my percentage will be the overall frequency, right? The overall frequency that I have, so that's 9 plus 7 plus 12 plus 2 plus 5, right? The total I have is 16 plus 12 is 28, so 35. So the total characters is 35. So for my percent, if I have 9 plastic, that means I have 9 plastic characters out of a total of 35. So I would do 9 divided by 35. And since it's a percentage, I would multiply by 100 and get 26% of the captured characters were plastic. And then 20% were wheat, 34% were insect, 6% were metal, and 14% were liquid. So this would be a simple frequency table that has my tally, my count, and the percentage of each class. So if we study the table, we can more easily see the distribution of the categories in the data set. So for instance, the insect category was most popular with 34% of the characters captured, and metal would be the least at 6%. So now this gives me a clear picture of what my data looked like. So if you were to go to a business meeting and just show him raw data, it's going to take him a while to count, to look, to understand, for you to explain. But if you present your data in this format, then people can easily see, oh, there were 9 plastic off the bat. They don't have to count. They don't have to do anything. Oh, it was 26%. So that means the total captured was 35, or, so it really brings out the information needed from the data that we have obtained. Now, grouped frequency distributions. Now, for this one, it's a little bit more broad, because a lot of times your categories aren't just your distribution, or your raw data isn't just simple enough to just make it into a simple basic tally table. So sometimes it becomes a little bit more polished. So this is an example. For example, on this slide and the next slide, these are the tables for the number of members of the United States Electoral College allocated in each state as the 2016 U.S. presidential election. So the size of the Electoral College for Alabama is 9 votes, California being the biggest at 55, Iowa, for example, 6, Maine is 4, Minnesota's 10, and then in the next slide we have the other states. We have Texas is 38, since it's a big state. New York is 29, heavily populated state. Utah 6, Vermont is 3, and so on. So how can we organize these into a frequency table, because each one of these has a different number. You can't just say, oh, I'm gonna put 50 states and then tally each state, and then but you're not going to be able to tally each state because some states have similar numbers. So then what are you going to do? Put, for example, like Nebraska and New Mexico together because they're both 5 with West Virginia. That's not going to work. So what we're going to do is a grouped frequency distribution where we're using a range of numbers instead of just a number. So we're going to be using a range of numbers to help us classify this information that we have. So the number of members of the Electoral College for each state is equal to the state's number of members of Congress. This District of Columbia also has 3 members. Most states have a winner take. So this is just overall information about what exactly an Electoral College is. When it comes to these type of problems, in so many stats problems, they'll give you, context. And sometimes it's useful, but most of the time it's just context to understand the problem, but this is not crucial to what we are solving. All right, so what we do is we will sort our table in order to help us see what we're looking at. So by putting it in order, now I can easily count how many 3s there are, how many 4s there are, how many 5s, 6s, 7s, and then I can see the minimum and the maximum number on this table. And that will be very useful. And what do I notice? I notice that my smallest number is 3 and my largest number is 55. So there is a gap of 52 numbers between the smallest state and the biggest state when it comes to the electoral votes. So first step to determine the classes is find the highest and the lowest value. So that is easily done by organizing your data. Second, find the range. And the range will always be the smallest number minus the largest number. So the range, right, is your max minus your min. So in this case, it was 55 minus 3, which is 52. Sorry about that. Equals 52. Select the number of classes desired. Find the width by dividing the range by the number of classes and rounding up. So let's see what I'm talking about. So the minimum we know is 3. The maximum we know is 55. The range is max minus the min, which is 55 minus 3, which is 52. So the range of numbers, span 52 numbers. 7 classes would give an average of a little more than 7 data values per class. So let me explain what I'm talking about here. So when I say you have to find the number of classes, sometimes the problem might tell you, create a frequency distribution table that has 6 classes or 5 classes or 7 classes or 8 classes. But sometimes it won't tell you how many classes. So you should, estimate which class you should choose. And normally you would choose between 5 and 20. The number is between 5 and 20. But you want to be, you want to give a good estimate of which number you want to choose. And the reason why I chose 7 was because I looked at the number 52, my range. I looked at my number 52 and I was thinking, if I choose 6, right? If I choose 6, 6, the closest number that divides 52 that is less than 52, right? That divides 6 that's less than 52 is 48. But then I thought of 49, which is closer to 7, right? That factor is 7. So I want to find a number that divides 52 that's a little less than 52. And the closest number that divides 52 that's close to 52, that is between 5 and 20, I found to be 7, because 7 divides 49. So by dividing 52 by 7, I can divide my classes into 7 classes, right? And I would have a 7.43 gap between each class. And it'll make more sense once I get to the actual table. But for now, anytime you divide the number that you found, and obviously if this divided 6, then I would have used 6 on this one, to be honest, but it doesn't. So I used 7. So for this class width, you have to always round up. always round up. So even if it's 0.43, which you would normally round down, we would round up. Okay, and the reason for rounding up is because we do not want to miss or skip any number. We rather be above than below, and it'll make more sense once I show the table. But first things first, once you find your class width, we start at the lowest class limit. That's where we start. We start at 3 because that's my lowest. So I'm gonna start at 3. I will add the class width, which is 8. And then I will add 8 again and again and again and again and again and again. So I'm gonna have 7 classes, right? 1, 2, 3, 4, 5, 6, 7. The 7 that I chose, with a class width of 8 between each one. So I am moving 8 units per, right? And then obviously 3 goes from 3 to 10. Why? Because 11 is next, right? So you wouldn't go from 3 to 11 and then start at 11 again. So you go from 3 to 10 and then from 11 to 18, which is 1 less than 19, and so on. So what you're doing is you're creating an interval of classes, so that now what I can say is how many states are between 3 and 10, how many states are between 11 and 18, how many states are between 19 and 26. And what also is crucial about this is the reason why I don't start at 11, right? The reason why I don't start at 11 or end at 11, my bad, is because what if a state has 11 electoral votes? Then would it be part of this class or part of this class? So therefore, I cannot go from 3 to 11. I have to go from 3 to 11, but I'm ending at 10, right? Also, there's one little issue that occurs, and we have to create something that is called a boundary. And what happens is there's a gap between 10 and 11. There's a gap. I mean, 10.1, 10.2, 10.3. Now, even though votes don't work that way, we cannot have a gap in our information. Because what if, right? What if? We don't know. So what we do at this point to create our boundaries is we will subtract 0.5 from the lowest and the highest. We will subtract 0.5 from the lowest, and add to the highest. I apologize. So we're going to subtract 0.5 to the lowest, add 0.5 to the highest. And the reason for this, right, we do that to all. The reason for this is now there is 0 gap, because I can go from 2.5 to 10.5 and I'm restarting at 10.5 to 18.5. Now you might ask, oh, but didn't you just say that we can't do something like this? Well, we know for a fact in our raw data, there is no 0.5 or 0.4s or 0.3. So we know that that won't happen where we have a common occurrence, right? So if there were a 0.5, then instead of subtracting 0.5 and then adding 0.5, we would subtract 0.05 or add 0.05 to the data. So if there were a decimal, then we would subtract 0.05 and we would add 0.05. However, because there is no, and these are all whole numbers, we can just add and subtract 0.5 to correct the boundaries to have no gaps. We cannot have gaps in any of our information. We have to understand that there is no gaps. Even if it cannot occur, we cannot have gaps. So this helps in avoiding any gaps. And then next, we want to tally our data. So how many data points are between 3 and 10.5? How many data points are between 10.5 and 18.5? So you just go back to your data set and you just count. There are 34 states. There are 11 states, 2, 2, 1, 0, and 1. So now that is our grouped frequency distribution table. That is it. Creating the limits, boundaries, and then our frequency. Now, to explain the part that I said it'll make more sense once we see our example of a grouped table. The class width being 8, right? The reason why it's very important to get the correct width and the reason why we round up, and remember, the correct width could work at any number. That's why usually the example will tell you how many classes they want. But if not given, why is it important to round up? Is because I rather end at 58, which we know that, California has 55, so why not end at 55, right? Why end at 58? By rounding up, I am assuring myself that when I'm done, I rather be my numbers a little above so it can contain 55 than for me to create my limits and reach 54, for example, where I would have missed out on that 155 for California. So it's very crucial to always round up when it comes to class width. You rather be a little bit above than to be below. All right. And a commutative frequency distribution table, you're going to need the table that you have here, which with your boundaries and your frequency. And the idea and how does this one work is that we're talking about how many states are going to be less than each of our boundaries. So we have 2.5, we have 10.5, we have 18.5, 26.5, 34, 42, 50, and our final boundary, which is 58.5. We're going to use all 8 of those, and we're going to see how many are less than each, right? And the idea is I have 34 states between 2.5 and 10.5. So how many are less than 2.5? Well, there's none that are less than 2.5 because I have 34 states between 2.5 and 10.5. Right? Now, how many are less than 10.5? So 10.5 or lower. How many are, that would be 34. So 34, which is 66% of my data. That's because 34 divided by 50. There are 50 states, right? So 34 divided by 50 is 66. Now, how many are less than 18.5? Now, you might think, oh, that's 11, the next number. No, that is 11 and less than. So 11 and the ones before it, which are 34. So that would be 45 states. So 45 divided by 50 is 88%. Then it's 2 states and the below. So that's 2 plus the rest because we're talking about less than, right? So every number from 26.5 and less, that would be 2, 11, and 34. And you just keep doing that and so on, right? So that is a commutative frequency distribution. So you're adding the states, you're adding the frequencies as you go. Commutative means to add. All right, now constructing a histogram. So a histogram is a graph that displays the data by using contiguous vertical bars. Unless the frequency of a class is 0, then there would be no bar there. A various heights to represent the frequencies of the class. Its purpose is to provide us with a graphical display of the distribution of a data set. So here is the example that we just did, and we are going to graph this using a frequency, using the histogram graph. So first things first is on a blank sheet of paper, you are going to put your class boundaries on the bottom, right? The class boundaries that you have 2.5 up to 10.5. And then from 10.5 up to 18.5. And on the y-axis, we're going to put our frequencies, right? We have up to 34, right? 34 is the highest. So normally if a number like 34 is your highest, you don't want to end at 34. You want to have some leeway just so that you can see an overall picture. Because if you stop at 34, then the peak of the graph is at the end of the paper. You don't want that. So you put a couple of numbers above it just so you could have some leeway so that the graph looks much, much more, cleaner. So to graph this, you're going to be using bars, but unlike regular bar graphs, this bar graph is telling you that it's from 2.5 to 10.5. So you're going from 2.5 to 10.5, right? So the range of your bar, right? The width of your bar matters because it's telling you from 2.5 to 10.5 all the way up to 34. Okay? And then from 10.5, just like on your boundaries, from 10.5 all the way to 18.5 was 11, and then 2, right? And then obviously this was, I think, 1, right? 1, if I remember correctly. I think this was 2. and then this was 0, and then this was 1, I think. So that's how your table would look. And anytime we see a histogram, there will always be a name associated with the shape of the histogram. So in this case, this looks like a J-shaped histogram, even though the J is facing the other way. This is considered a J-shaped histogram. So the shapes of the distributions of our histograms. The most important ones are these three: bell-shaped, positively or right skewed. So sometimes you might see it written as right skewed shaped, or positively shaped, or negatively skewed, or left skewed. So it is important to be able to recognize the shapes of the data distribution, especially for latter chapters. The shapes of the distribution usually determines the appropriate method that a statistician should use to analyze the data. Distributions are most often not perfectly shaped. It is not necessary to have an exact shape, but rather to identify the overall pattern. So it's very important to say things like roughly right skewed or left skewed or roughly bell shaped, because to have a perfectly right shaped or a perfectly bell shaped graph is very unlikely to happen. You will always have numbers that kind of screw up the graph to be a perfect bell shaped or right skewed graph. So a bell-shaped distribution has a single peak and tapers off either end, and is roughly symmetric on both sides of the line running through the center. So here's a bell-shaped. So again, this is not a perfectly symmetric bell-shaped, because you can clearly tell that this peak is higher than this peak is higher than this peak, but this is roughly bell-shaped, right? It looks like a bell. So this is roughly bell-shaped, and this is a graph that you can say is a bell-shaped distribution. And negatively skewed when the data values are clustered to the right and the taper off to the left. So meaning, as you can tell, they're all kind of to the right of the graph, and then it's going down towards the left, right? So it's kind of like skewing towards the left. It's falling towards the left while it's increasing towards the right. So this would be a left skewed. So you could imagine what a right skewed would be. It's the opposite, right? When the peak of the distribution is to the left and the data values taper off to the right. So this would be a right skewed. And keep in mind that a right skewed and a J-shaped kind of look the same, but normally people don't talk about J-shaped. If you see a J-shaped, you would normally say roughly right skewed. But this is a right positively skewed or right skewed distribution. And there are 4 others: J-shaped, reverse J-shaped, bimodal shaped, and U-shaped. So here is a U-shaped. You can see that it kind of looks like a U. Here's a J-shaped. As you can see, it is, similar to a positively skewed, but if you look at it, it's kind of, more evenly out, right? It's more of an even shape than a right skewed, because a right skewed could, just like taper off like that. It could be a very high peak compared to the rest. While J-shaped is they're more near each other as it goes down. And then reverse J-shaped is the same as the right J-shaped, just the opposite side. And a bimodal is a distribution with 2 modes, because if you look at your classes, a bimodal, and we're going to see this in chapter 3, is a data that has 2 modes. So a mode is a number that repeats more than once, right? The mode of a class or a mode of a distribution or a data is the number that repeated the most. Okay, so let's say I have a data of 1, 2, 2, 4, 5. 2 repeated twice. 2 is the mode of this data set. But say I have 3, 3. So now I have a bimodal class. I have a class with 2 modes that repeated the same amount of times. So in a bimodal distribution, that's just telling you that there are 2 classes with the same number frequency. So it's a bimodal distribution. And to know the mode of your class or the mode of your distribution, it's the one with the most frequency, right? All right, now we're going to speak about some other types of graphs. We're going to be speaking about some pie graphs, bar graphs / Pareto graphs, which are pretty much the same, just a minor difference. Time series graph, dot plot, and a stem and leaf plot. So first things first is a pie graph, and the variables for a pie graph is nominal and categorical. That is very crucial because in a pie graph, you cannot have both be categorical, because then you wouldn't know how big of a size of the pie graph is, right? Because each category has a specific size of a slice, and if they're both categorical, then it wouldn't work. A pie graph is a circle that is divided into sections according to the percentage of frequencies in each category of the distribution. So let's look at an example. So an example, constructing a pie graph. So this frequency distribution shows the number of pounds of each snack food eaten during the Super Bowl. So we're going to construct a pie graph data. So first things first is we got to look at our data here. So potato chips, 11.2 million, right? Tortilla chips, 8.2 million, pretzels, 4.3 million, popcorn, 3.8, 2.5, for a total of 30. So to construct a pie graph, we need the percentage of our frequencies. So the way to do this is we can either use the degrees formula or we can use the percentage formula. Now, depending on what the question is asking you, right, they might tell you how large is the slice, or the proportion. If they ask for the proportion of the slice, then they're asking for a percentage, right? If they're asking for the angle, then you would use the degrees. And pretty much the formula is the same. You take the frequency, which is 11.2, you divide by the total, which is 30, right, your n, and then you either multiply by 100 if you're looking for the percentage, or you multiply by 360 if you're looking for the degrees, and you found yourself your first slice. And then you do that for the next 4, right? And then once you do all that, you will get this here, 8% for nuts, 38% for potato, 27% for tortilla, 14% for pretzels, and 13% for popcorn. And obviously you have to kind of eyeball it. This type of pie graph, you would have to eyeball it. I mean, 8% compared to 13% is a little bit more than half the slice, right? You just kind of have to eyeball it. That's why it's very good to use the degrees formula, because you could, with the degrees formula, you could get the actual degree of this, for example, right? Potatoes 38%, but I know that this might be, let's say, 120 degrees. So I know how to draw a 120 degree triangle in a sense, right? You're drawing an angle, but think of it as you're drawing a triangle, right? But instead of actually connecting the two ends, you're kind of going in a circle fashion, right? So think of it as a triangle, but you're just creating an angle, and then you're connecting them with an arc, not a line. A time series graph represents data that occurs over a specific period of time. So obviously, hence the name time series. The data shows the average cost in millions of an ad during Academy Award shows. So in millions. So an ad cost $1.4 million in 2016, 1.55 in 2017, 1.6 in 18, and 1.78, and then 1.90. And as you can tell, it's increasing with time, right? So in a time series plot, okay, what you do is you always put the time on the x-axis, always, and then your y is your variable, whatever it is, right? In time, is it cost, is it, no matter what it is, you just put the time on the x-axis and your category, whatever your y is, on the y-axis. And in some cases you might be able to compare two separate aspects in one time series graph. For example, the Academy Award show versus the Super Bowl ads, right? So Super Bowl is going to be the purple and the Academy Award is going to be the green. And you'll see that, for example, the Super Bowl was more expensive in 2016 and then it kind of dipped in 2017, the price, and then it resurpassed the Academy Awards in 2018 and just kept going up and up, right? You could kind of compare two separate graphs or two separate categories into one time series graph. So it is possible to compare in a time series graph, unlike a pie chart, right? In a pie chart, it's a little harder to compare, but in a time series, you can. All right, bar graphs. A bar graph uses qualitative data using horizontal or vertical bars. Example, the table shows the average money spent by first-year college students. So they spent $728 on electronics, $344 on decor, $141 on clothing, and $72 on shoes. And the way a bar graph is drawn, right? You could, if you are doing a vertical bar chart, then you would put the categories on the x-axis and the sizes of each bar on the y-axis. And if you are using a horizontal bar graph, you would put the categories on the independent variable on the y-axis, and you would put the dependent on the x-axis. So as you can tell, these are exactly the same. These are exactly the same graph. The only difference is one is vertical and one is horizontal. And just to make a note about Pareto graphs, this here is a bar graph. It is also a Pareto graph. And the reason why is because a Pareto graph is a bar graph in decreasing order. So when you want to draw a Pareto graph, it is a bar graph in decreasing order. So you organize them from highest to lowest. So you're kind of in a decreasing order, or it could be in order of increasing order. Doesn't matter. The idea is you order them, because sometimes a bar graph could be something like, oh, I could put dorm decor here, I could put electronics here. It's still a bar graph, right? It's still a bar graph because I could switch this and this. It's still a bar graph. However, it's not a Pareto graph anymore. To be a Pareto graph, you have to put your bars in order. That's the only difference between a Pareto graph and a bar graph. There's no other difference. All right. And in a bar graph, you could actually compare as well, just like the time series graph. So if you look here, we're going to compare males versus females. Males are going to be the light green and females is going to be the pink. And you'll see here that, we can compare by drawing two separate bars near each other. And we could say, oh, males spend more on electronics, females spend more on decor, they spend more on clothing, and they spend less on shoes, for example, right? So you could also compare using bar graphs. All right, a stem and leaf plot. A stem and leaf plot is a data plot that uses part of the data values as the stem and part of the data values as the leaf to form groups or classes. So at an outpatient testing center, the number of cardiograms performed each day for 20 days is shown. Construct a stem and leaf plot. So here we have raw data. We have a bunch of raw data. So what we're going to do is we're going to order and arrange our raw data and look at what we have. We have 2, 13, 14, 20, 23. So we have quite a few 20s. We have quite a few 30s, right? We have quite a few 40s and a few 50s. So the way this is done is we're going to take the first number of each one we have. And for the 2, it's just going to be 0, 2, right? So we're going to take the first number, and that is what my stem is. The first number is my stem. This is my stem here. And here's my leaves. So 0, 2, that's only one. I have 1, 13, and I have a 14. I have a 20. I have a 23. And I have a 25. I have a 31. I have a 33. I have a 32. I have another 32. I have another 32. And another 32. So you could tell that's the mode, right? That's the mode. (32) is the mode. And likewise, that's all it is. You take the first number, so the 10th digit, and you put that as your stem. And then you take the leaf would be your ones digit. and you got yourself a stem and leaf plot. If you want to compare using a stem and leaf plot, even though I may not have shown this in this example, say there's another form of data. Say we have, like 0, 3, 1, 4, 1, 5, 2, 2, 2, 3, 3, 4, 5, 4, 4, 4. Say we have that. The way you would do another stem and leaf plot, that on the same stem and leaf plot, you would put another line here, and you would put 3. There's a 1, 4, and a 1, 5. There is, well, sorry, you would put them in order actually. So this is how you would compare. So 4, 5, and then we have a 2, 3, and a 2, 2. So that's 2, 2, and a 2, 3. We have a 3, 4. We have a 4, 4, and we have a 5, 4. So this is how you would compare. You would just put another line to the left of your stems and then create another branch of leaves. If you had two separate datas and you had to compare them. And lastly, dot plot. A survey given to students of how long does it take them to eat lunch has these results. So it takes me no time to eat my lunch, meaning they don't even have lunch. 3 people. It takes me 1 minute, 2 people. Takes me 2 minutes, 3 people, and so on. So the way a dot plot is done is as simple as this. So at time 0, right, I have 3 people. So the count is going to be my dots. I have 2 people for 1 minute. So you're just putting dots. You're just putting dots. That's all it is. So you put a time. You put a time bar, and then you just put your dots as I'm putting them. Then you got yourself a dot plot. And a nice thing about the dot plot, which is very, very useful, what's very useful about a dot plot is you could actually see it look like a histogram, right? You could kind of see that this is definitely not a, you could see if it's right skewed, left skewed. You could see if it's normal or not, but you could see it's kind of not. Maybe this could be roughly normal. I wouldn't say it's roughly normal. It's kind of doesn't really have a shape. But normally in a dot plot, you could actually see the shape of the data that you're looking for, as well as the stem and leaf plot that we just had, right? We just had a stem and leaf plot, right, that kind of had numbers like, like this, right? Kind of had numbers like this. And you could look at it sideways and say that this is actually a normal bell-shaped distribution, right? So there's actually multiple ways to see the distribution. It doesn't have to be just a histogram. So these graphs can as well show the shape of our distribution as well. And this is it for chapter 2. Pretty much. We're going to be doing chapter 2.4 later on. So skip 2.4 for now, and we'll be doing that later on in the semester. So we're going to be skipping that for now.